Every year, in the heart of Zambales, a remarkable natural phenomenon quietly unfolds. Beneath the lush mountains and along the rugged coastline, the earth itself breathes out a hidden treasure, hydrogen gas, pure and potent, rising invisibly into the morning sky. The Philippines loses an astonishing 808 tons of nearly pure hydrogen gas into the atmosphere every single year. This isn't just any gas. It's a clean, renewable fuel source, naturally produced and completely overlooked for decades. Imagine the potential, a resource that could transform the nation's energy landscape, simply drifting away, untapped and unnoticed. That's enough clean fuel to power thousands of homes, energize bustling factories, and support small industrial grids across the country. If harnessed, this hydrogen could provide a stable, sustainable energy supply, reducing our dependence on imported fossil fuels and cutting harmful emissions. Yet, until now, this opportunity has remained out of reach. No drilling is required, no invasive mining. The land remains untouched, its beauty preserved. There are no noisy rigs or scars on the landscape, just the silent escape of energy into the air. There's no need for complex supply chains stretching across continents, no reliance on Middle Eastern oil tankers, and no vulnerability to global market shocks. Instead, we're watching a valuable resource simply leak away day after day. But change is on the horizon. In 2026, the Philippine government is fast-tracking a bold 15 billion peso hydrogen roadmap. This ambitious plan aims to capture, contain, and utilize this abundant energy source, turning what was once wasted into a cornerstone of the nation's clean energy future. The stakes are high. Will this be the dawn of an energy revolution that powers progress and protects the environment? Or are we on the verge of engineering a new kind of disaster? The answer lies in how we choose to act, right here, right now, in Zambales. On February 11, 2026, the Department of Energy released a circular outlining a national-level roadmap for hydrogen development. The plan isn't just about funding, it is about technical readiness, engineering standards, and industrial-scale infrastructure. Hydrogen is officially on the fast track. Headlines focus on the 15 billion peso budget, but engineers and technicians are asking something more critical. Do we even have the materials, the knowledge, and the systems in place to contain and purify this naturally occurring hydrogen without catastrophic loss? The Malampaya gas field in Palawan is a marvel of engineering, but it comes with significant challenges. Extracting natural gas from beneath the ocean floor requires massive offshore drilling platforms, advanced technology, and a complex web of logistics. Engineers, geologists, and workers must coordinate around the clock, often in harsh and unpredictable conditions, to keep the operation running smoothly. The process is not only expensive, but also demands a high level of expertise and constant maintenance to ensure safety and efficiency. In stark contrast, the province of Zambales offers a unique and naturally accessible source of hydrogen. Here, the landscape is dominated by rugged mountains and rolling hills. But unlike offshore sites, these resources are found right at the surface. There's no need for deep-sea drilling or complicated infrastructure. The terrain is open and accessible, making exploration and extraction far simpler and more cost-effective. This natural advantage positions Zambales as a promising site for future hydrogen production. The secret lies within the Zambales ophiolite, a vast geological formation that dates back millions of years. These ophiolites are slices of the Earth's oceanic crust and upper mantle that have been thrust onto land. They are rich in minerals and provide a rare window into the planet's deep interior. Geologists from around the world come to study these rocks, fascinated by their unique composition and the clues they offer about Earth's ancient history. Over countless millennia, powerful tectonic forces pushed these mantle rocks up from the depths of the Earth to the surface. The process involved the collision and movement of massive plates shaping the dramatic mountains and valleys we see today. This geological upheaval exposed rocks that are rarely seen above ground, creating a natural laboratory for scientific discovery and resource exploration. When rainwater seeps into the cracks and fissures of these iron-rich rocks, it triggers a remarkable chemical reaction known as serpentinization. This process transforms the minerals within the rocks, releasing energy and producing hydrogen gas as a byproduct. The reaction is entirely natural, requiring nothing more than water and the right type of rock. It's a slow but steady process that has been occurring for millions of years, quietly generating hydrogen beneath our feet. Scientists have discovered that the hydrogen gas produced in Zambales is of exceptional purity, almost 99% in some samples. In laboratories, researchers carefully collect and analyze these gases, using advanced equipment to measure their composition. The high purity of this hydrogen makes it especially valuable for a range of industrial and energy applications, from fuel cells to clean energy production. This naturally occurring hydrogen is known as white hydrogen. Unlike hydrogen produced through industrial processes, white hydrogen forms deep within the Earth's crust, trapped in rock formations and released through natural reactions. Scientists around the globe are now racing to understand its potential, as it could revolutionize the way we think about clean energy. However, tapping into this resource comes with its own set of challenges and unanswered questions. Hydrogen is the smallest molecule in existence. It is lighter than air. It escapes through microscopic gaps in steel. It leaks through weld imperfections. It seeps through seals designed for methane. Even advanced containment systems must account for this. If you think you can just capture it, you are underestimating physics, metallurgy, and engineering precision. The gas escaping from the Nagsasa seep isn't perfectly isolated. In fact, what you see bubbling up from the ground is a natural mixture, not a pure stream of hydrogen. This seepage is a fascinating phenomenon, but it also presents a unique set of challenges for anyone hoping to harness it as a reliable energy source. As the gas rises, it mixes with nitrogen from the atmosphere and, at times, contains trace amounts of methane and other minor gases. This creates a complex and variable gas composition that must be carefully analyzed and understood before any commercial use. Scientists and engineers spend countless hours in the lab, running tests and calibrating equipment to determine exactly what's in the mix and how best to separate it. To make this resource commercially viable, you need advanced on-site pressure swing adsorption units. These are specialized machines designed to separate hydrogen from the other gases with high efficiency. Installing and maintaining these units is no small feat. They require precise engineering, regular calibration, and a deep understanding of the local gas chemistry. This is where billions of pesos will be invested, not in searching for new gas seeps or drilling deep wells, but in building robust high-pressure purification facilities. And all of this must happen in some of the most challenging terrain in the Philippines, rugged, rocky, and often remote. The logistics alone are daunting, requiring heavy machinery, skilled labor, and careful planning to ensure the infrastructure can withstand both the environment and the demands of continuous operation. If your separation units aren't perfectly optimized, you risk losing hydrogen purity at every stage of the process. Every percentage point of lost purity translates directly into lost revenue and reduced energy output. That's why constant monitoring, testing, and fine-tuning are essential parts of daily operations. And lost purity doesn't just mean a minor setback, it means lost value, lost energy, and in many ways, a partial failure of the entire project's promise. The reality is, the success of hydrogen production here hinges not just on what's underground, but on the strength and sophistication of the infrastructure built above it. And then comes the most critical engineering challenge: hydrogen embrittlement. Hydrogen atoms are so small, they can migrate into the lattice of metals, changing their molecular structure. If standard carbon steel is used in pipelines or storage vessels, it becomes brittle over time. Not gradually, not predictably, catastrophically. Fractures appear without warning. Weld joints fail. High-pressure lines rupture. And here's the most terrifying part. A hydrogen flame is invisible in daylight. You won't see it. You won't smell it, you won't feel it until damage has already occurred. This is why material selection, welding quality, and ultrasonic leak detection are not optional. They are mandatory for safety, economic viability, and long-term success. This project demands high-nickel alloys. 316L stainless steel is the minimum standard for most pipelines. Advanced ultrasonic leak detection is required for early warning. Disciplined preventive maintenance schedules must be strictly followed. The 15 billion peso roadmap is not just funding, it is a test of Philippine engineering maturity. Whoever implements it correctly will set the standard for sustainable hydrogen utilization in Southeast Asia. If Zambales succeeds, it could reduce liquefied natural gas imports, it could complement Malampaya, it could position the Philippines as a leader in white hydrogen development in the region. But if corners are cut, the cost will not just be financial. If you are an engineer, technician, or energy analyst, comment your biggest technical concern below. Let's make sure the 15 billion pesos doesn't become 15 billion pesos lost to physics. Don't forget to subscribe and click the notification bell to catch the next breakdown video. Thanks for watching the entire video.